Hi. So, in this video, I'm going to discuss the hard questions in SLMC 4 paper given last year, and that was the first paper in SLMC 4 as it was introduced last year. So let's look at the hard questions. Okay, hope you can see the questions. The first, the front page, it is shown to you for your information, right? So as you can see, this question paper has 30 multiple choice questions, and first 10 are easy, second 10 are medium, and third 10 are hard. And as you can see, the scoring system depends on the difficult level of the questions. So these questions are given 5 points each, and the medium questions are given 6 points each, and the hard questions are given 8 points each, right? Okay, so let's look at the questions. Right, the first question. Let me check whether my pen color is what I want. Yes, right. So, number 21. How many different numbers can be made by rearranging the digits in the numbers? In the number, should be number 1 to 1234. We need to count the number 1234 too. So this is a 4-digit number, right? It has 4 digits, right? And you're allowed to interchange, rearrange the digits, and then you get different numbers. For example, so this is 1234. And if you rearrange the 1000 digit and the hundredths digit, you get 2134. So that is a new number. So likewise, how many different numbers you can make? That's a question, right? Before I do this, I want to actually draw the similarity of this question and the question in the medium section, right? That was actually to find the number of ways of arranging apple, banana, and mango. So we use letters to denote those fruits, right? A for apple, B for banana, and M for mango. And we found that there are 6 arrangements, right? So I can quickly write the arrangements, and starting with banana. So let's write the B nicely, and A, M, B, M, A, and then starting with mango, M, A, B, M, A, B. So there are 6 arrangements. Now, if you take 3 digits, right? Let's say, so if you take the number 123, and how many numbers you can make by rearranging the digits in this number? So this question actually, I change it to, I ask the same question for 123, right? So it is the same answer that we got in this arranging apple, banana, and mango, because there are 3 things, like, and we also have 3 digits here. We need to rearrange, put them in different orders. So there are 6 ways of doing this, right? 6 ways of doing this, right? Now, in the given problem, we have 4 digits, right? Now, we can start with the 1000th digit, right? It has 4 choices. So we can start with 1, right? And then we have the digits 2, 3, 4. And we can rearrange these 3 digits in 6 ways. Starting with 1, there are 6 numbers, right? 6 numbers. So I'll write them quickly. So 1,243, 1,000. Now we start with 3, 1,324, 1,342, and then we start with 4, 1,423, 1,432. So let me, yeah, so it should be, yeah, that is nice, right? So there are 6 of them, right? And also, if you let 2 to be the thousands digit, again 6 numbers, right? And with 3 as a thousands digit, again 6 numbers. And with 4 as a thousands digit, again 6 numbers. So there are actually 4 times 6 arrangements, 24, right? And of course, that answer is B, 24, right? So as you can see, we used a problem we solved earlier, right? Actually, in the same competition in the easy section, sorry, in the medium section. So this sort of thing, what the mathematicians do. So you need to imitate them, right? How they think, how they solve problems, right? So, so the number of arrangements is 24, right? Now let's go to the next question. Meena thinks of a number, multiplies it by 10 and adds 7 to the answer. She gets 77. What's the number she thought? Now, if you think a little bit about this problem, right, we can use the strategy of working backwards. So usually we work forward, right? But sometimes we going to work backwards depending on the problem, right? So here, so we start with what she got, the 77, and then that actually she got by adding a 7 to the previous result. So if we subtract 7 from 77, right? So let's draw a diagram here so that we can see what's going on, right? So let me get space here, right? Now she thought of a number we don't know, with the question mark, right? So let's put that question mark in a box, right? And then what she does is that she multiplies this by 10. So this is her action, and then we don't know the result, right? Again, we don't know. And then to that result, she adds 7, and then we know the result, right? Which is 77, right? Now we go backwards, right? So we have 77, and we work backwards, right? And then we can find this number by reversing what she did, right? You need to reverse what she did. So we subtract 7. So we get 70 here. And then to get the number she thought at the beginning, right, we need to do the reverse of multiplying by 10. So that is actually dividing by 10. So we get 7, right? And we can check, right? So when you multiply 7, so we can actually put that 7 into the box in this forward flow, right? So let's erase these 2 question marks, right? And then we can write 7 here. So we get 70 here. And if add 7, you get 77, right? So you can see that, it worked very nicely here. So you need to remember the strategy, work backwards, right? Normally, you're told that you always have to go forward, right? And then here, you need to work backwards. But actually, This is different, right? It's a strategy which can work. Right? This is not going backwards, right? Of course, we work backwards, right? But there's a difference. All right. So let's go to the next question. So number 23. So in the figure below, any two regions with a common boundary should be colored in different colors. What is the minimum number of colors needed? So first of all, we need to understand what this question asks, right? So we are given a figure and we can see some straight line segments, and then there are regions bounded. Bounded means that, like fence, these straight line segments, they bound the region on the paper. Now, this you see and here on my screen, and if I put this on my paper, so it bounds a region, right? So this is actually nothing new, right? Because I think you must have colored a world map or some kind of a map, just for fun, right? So you have like different countries with a common border, and then you need to show the countries separately. So use different colors. If they have a common border, different colors. The same thing here, right? But instead of countries, we have regions bounded by straight line segments. Now, the world map is not like that, right? The boundaries are not straight line segments, right? All kinds of curves are there, right? But the same thing. So if two regions have a common boundary, we color the two regions in different colors. For example, let's color this square, the smallest square, right? Here in red color. Let's read. Then this triangle we color in blue. Now, if you take, I put a dot here. So if you look at, this one, right? It actually has a border with the region colored in blue and the region colored in red. So we can't color this, where dot is, that region we can't color in blue or red. So we need to use a different color. So yeah, let's use yellow, right? Now, if you look at the region in where I put a dot right now, it actually borders with the red region and the yellow region. So there's no problem in coloring it in blue, right? And now I'm going to put a dot here. And in the region that I just put a dot in, it actually has a border with blue region, red region, blue region. So we can color it in yellow color, right? Because we don't want to waste colors, right? So we want to use the minimum colors, right? For example, if you take the world map, I think there are about 180 plus countries. So you don't want to use 180 colors, right? So you want to use the minimum number of colors, right? So now we have managed to color all the regions in red, blue, yellow, three colors. So what about the region? Now I just put a dot in, and what is, so that region, what color? So it borders with blue, yellow, right? Those two colors. But it doesn't border the red region. So that means we can color this in red. So we can color the whole, right, map. So let's call it a map, right, in three colors, right? The answer is 3. Okay. Okay. So let's look at the next question, number 24. As I always say, you have to do the problem before I discuss it, right? So pause the video and work it out, and then check what I do. Okay. So how many two-digit numbers have units digit 1 or 2? So units digit is another name for the ones digit, right? Ones digit, right? So, so we have two choices for the ones digit. So if I draw two boxes, right, for the tens digit and the units digit or the ones digit, right? The ones digit box can have only two digits, 1 or 2, right? But the 10th digit one can have not 10, only 9, right? Because if you put a 0, it is not a 2-digit number, right? So we can put 0 in the 10th digit box, right? So you can put 9, and with units digit 1, right, we can put 9 numbers there. So we have 9 numbers ending with 1, right? And then another 9 ending with 2. So the total is 18. So we can actually, so there are 18 two-digit numbers ending with 1 or 2. Okay, right. So let's move on to the next question. Manit's age in years is an odd number less than 15. And 1 more than his age is a multiple of 5. What is his age? So this is not that hard, right? We know the odd numbers less than 15, right? Now, how many are there? So to look at the even number next to 15, bigger than 15, which is 16, half of them are odd numbers. So there are 8 odd numbers. Let's say 1, 3, 5, 7, 9, 11, 13, right? So you can see, so there are 7 odd numbers, right? But I forgot 15, right? This is less than 15. So 15 is not included, right? So actually, we should have looked at, the even number less than 15, which is 14, half of that is actually 7. So there are 7 odd numbers, right? 7 odd numbers, 7 even numbers from 1 to 14. And so it is less than 15. So 15 is not included. And 1 more than his age is a multiple of 5. Now, here now we are given the choices, right? 5, 7, 9, 11, 1. So all those numbers are in here, right? So we just need to check at what each of these choices, right? And see whether it's a multiple of 5. So you can see that only 9 satisfied that condition, right? When you add 1 to 9 is 10, multiple of 5. Others are not. So 9 must be its age in years. Okay, right. So we go to the next question. Praveen and Pavani have the same number of marbles. If Praveen gives 3 marbles to Pavani, and then how many more marbles does Pavani have more than Praveen? So at the beginning, right, they have the same number of marbles, right? So Praveen, so let's say that Praveen and Pavani, right, they have the same number of marbles, right? And then Praveen gives 3 marbles to Pavani, so his number of marbles decreased by 3, right? So now he's here, right? And then Pavani's number increases by 3. So he is here, she is there. So then what is the difference between their numbers? So you can see that it is actually 3 plus 3, 6. You might think that immediately, right, it must be 3 because Praveen gave 3 marbles to Pavani. So then Pavani must have 3 more than Praveen. But the problem is that Praveen actually lost 3 marbles, right? So therefore, it is not 3, it is 6, right? So we were able to do that using a diagram. So you can see that drawing a figure is a very powerful strategy, right? Drawing a figure, right? Now, earlier, I talked about this working backward strategy. Here, drawing the figure, right, is also a very uh, uh, powerful strategy, right? Now, you might also do this in a different way, right? So let's say that Praveen, the number of marbles Praveen has, we don't know what the number is. Let's say that Praveen has A number of marbles, right? Pavani has B number of marbles, right? So Praveen gives 3 marbles to Pavani, so he loses 3 marbles, right? And then Pavani gets 3 more marbles, so she has now B plus 3, right? Now it's get a bit mathy, right? To find the difference, right? With the number that Pavani has more than Praveen, you need to subtract what Praveen has, right? Which is A minus 3 from B plus 3, right? Now this, of course, right, is you cannot do this. You have to learn numbers with the minus sign, right? So therefore, I'm not going to do this. Okay. Um, all right. Now it says that Praveen and Pawnee has the same number of marbles, right? So A is equal to B, right? So we are adding. So it's like still, I think I'm going to leave it to you, right? Maybe you can think about it, how to do it, right? So as I told you in one of the videos, right? Maybe the easy one or the medium one, right? We cannot find answers to all the questions, but we should not stop asking questions, right? So we should have to keep our list of questions which we haven't found answers, and you need to keep trying to find answers. So this is, I'm going to leave it to you. Put that in your list, right? Think. Okay, let's go to the next question, right? Where is the kangaroo? Well, kangaroo seems to be trapped somewhere, right? And there's a circle, square, and a triangle. Now, where exactly kangaroo is trapped, right? So that is what we need to figure out here. So we can see that the kangaroo is outside the circle, right? He's outside the circle because if you actually shade the circle, right, inside the circle, you can see that, well, kangaroo is not there, right? So kangaroo is outside the circle. So you need to remove all these inside the circle, right? They can't be the answer inside the circle. No. Inside the circle. Yeah, those are the ones actually. And then you can see that. Now let me erase this. And let's color the triangle, right? And when you color the triangle, you can see that even the kangaroo gets colored, right? So that means kangaroo is in the triangle. So let's check, inside the triangle. So if it is outside, then not inside. So it can't, anyway, it is not, we have cut it out. So it says D not inside the triangle. So it can't be, right? And here, right. Okay, now we have the two choices, C and E. right? Right. So let's check uh, uh, whether the kangaroo is inside the square or outside the square, right? So let's color it, the square. And when you color it, you can see that even the kangaroo gets colored. That means it is inside the square, right? So this says not inside the square. So that is this is also out, right? So therefore, the answer is C. Inside the square, inside the triangle, but not inside the circle, right? So here actually we so that inside of a region and outside of a region, like in the early problem, the maps, right? So it's also like a map, right? You have a C circle and a square, right? And a triangle, right? So it's also like a map, right? And then so we have regions, right? So the region inside the circle, region outside the circle, right? And now think about this, okay? As I told you, just finding the answer is not enough. We need to think beyond the answers, right? Like mathematicians do. Okay, let's go to number 28. I can't see my pen. Let's see where is it. Sometimes. All right. Now I see 28. Sita has a rectangular bar of chocolate with lines drawn parallel to the sides, forming small squares. Yeah, we know these chocolate bars, slabs. And she shares it with her sister by breaking off an entire row of five small squares. So she actually breaks an entire row, right? So must be um, row, yeah, with five small squares. Remaining chocolate bar has 35 small squares. So remaining chocolate bar on the slab, right? So now that means that so row columns we can think of now before she broke off this row five small squares, right? How many columns were there? Well, five columns, right? Five columns, right? And how many rows? So the one row she broke and gave it to her sister, right? So then uh, now the remaining one, this is the remaining one, right? So it says that the remaining one, right, has 35 small squares. So let's use a different color. So this side, so there are five, right? Five squares. And this side, how many? So whatever that number, its product should be equal to 35. So that means there are seven squares here, right? And actually, you don't need to actually find the seven, right? Because if this area has 35 and here you have 5, right? It is actually 40, right? It is 40, right? So as you can see, right, sometimes you may work in certain direction, right? And then you suddenly say, well, I don't need that. So we don't need to find, right? This number, right? Because 35 plus 5 is 40. So, but then to think beyond the answer, we can see that, well, this uh, 35, so there are seven uh, rows in that slab, and altogether there were 8 rows, right? 7 plus 1 is 8. Okay, let's look at question number 29. When each of the digits 3, 4, 5, and 6 is placed in a square below, that means we need to use all of these digits, right? It's not 3, 4, 5, or 6, right? So we had to use all 4 digits, right? Put one each into these 4 boxes, and then we get a 2-digit number here, 2-digit number. So this is 2, and here another 2-digit number. And this says that sum of 2-digit numbers, you add them up. So what is the largest possible sum? Right? So we can write all the possibilities, combinations, whatever, right? And then find the sum, and then we can put them in the ascending order and pick the first one, or the descending order, ascending order, you pick the last one, right? And you put them in the descending order, you pick the first one. That's the largest one. But without doing that, we can do that because we know that 2-digit numbers, right? So it has a tens digit and a ones digit, right? Now, the tens digit actually gives it more weight, right? What is the digit in the tens place? It gives 10 times that, right? So when we determine the largest possible sum, right, for these 2-digit numbers, right, for the tens digit, we put the largest 2 digits. That way we actually maximize the sum, right? So what are the largest 2 digits out of these 4? So those are actually 5 and 6, right? So we put a 5 here and a 6 here, right? So from this 5, we get 50 to the sum. And from this 60, this 6, we get 60, right? To the sum, right? And then we put the other 2 digits in the ones place, 3 and 4, and they actually bring only 3 and 4, right? So what is the sum? It is actually 100 and, so this is 110, and this is 7, so it is 117, right? So the largest possible sum is 117, and as you can see, here we actually, our thinking is at a high level, right? Because now we have a very good understanding of the place value system, and so we can actually think using those concepts, place value, because we look at the tens digit, they give the weight, they make the sum bigger, right? So that's how we figured out, right? Now, if you didn't understand, don't worry. We'll try again and come back and watch the video again. Right? Okay, so let's go to the next question, the last one. The farm has a total of 25 chickens and rabbits total, right? Their legs add up to 86. How many chickens are there in the farm? So now if you use letters to record the information, so C for chicken, C, and R for rabbit, so we can write C plus R is 25. And what about legs? So chicken's legs. So CL, chicken legs, and rabbit legs are L. So this is 86. Now, how do you find the number of chickens? Right. So we can actually, now this way, you can think how to how to go like this, proceed like this. But we will make a table and solve this problem, right? So we make a systematic list, right? So we have chickens and rabbit. So let's make a table. So one column for chickens, C, one column for rabbits, R, right? And one column for their legs, right? Legs, total, right? The total has to be 86. So we can start with one chicken, right? One chicken. So that means 24 rabbits. How many legs? So 24 times 4 plus 2. The chicken has only 2 legs. So what is 24 times 4? That is, so I'm going to do this. So 20 times 4 is 80. 4 times 4 is 16. So it is 96. Plus 2, it is 98. Right. It is not 86. So we keep working. 2 chickens. Right. So then 23 rabbits. So how many legs? So 23 times 4 is, so this plus 2, so this, actually this plus 4, right? It plus 4, so that is, what do we get? So 23 times 4 is 80 plus 12, so 92, plus 4 is 96. Is that correct? So 80 plus 12, 22. Plus 4 is 96. Again 96. Right. So 3 chickens and 22 rabbits. Right. So here, earlier actually, it was 98. Right. Now this is 96. Okay, we'll find the number of eggs. When we have 3 chickens and 22 rabbits. So 22 rabbits. So 96, 92, it should be 4 less, right? 1 rabbit less. So that is actually 88. Plus 1 more chicken. So 6. What do we get? So this is 494. Now we see a pattern, right? So when the chickens increase, right, the number of legs decrease, right? So now that should give us an idea, right? So when we have 1 chicken and 24 rabbits, if the number of legs is 98, right? And we want to have the 3 dots, continue, 86 legs, right? So this has to drop to 86 by how much? So it has to drop by 12, right? Drop by 12, right? Drop by 12. And so each drop actually, right? Drop by 2, right? So how many chickens actually, we need to increase? So 12 by 2 divided by 2 is 6, right? So we had to go from 1 chicken, right? We need to increase it to 1 plus 6, 7. 7 chickens, right? So 7 chickens, that means how many rabbits? So 18 rabbits, right? So 7 times 2 is 14, and 18 times 4 is what? So that is 10 times 4 is 40, plus 8 times 4 is 32. So this is 72, and 70 plus 14 is, right, if you add them up, you get 86, right? It's 86. So the answer is 7 chickens. 7 chickens, right? Right. So we made a systematic list, right? Systematic list. And we made a key observation to reduce time, right? We did not waste time by going all the way from 1 to 7, right? We found a pattern, right? So look for a pattern is also a strategy. So we found a pattern and we used it to reduce time, right? We go from 1 to 3 straight to 7, right? So that's good, right? So is this the only solution? Is there another way of doing it? Yes, there is, right? I'll show it to you. And then I'll ask you to do a variation of it, right? Okay, this is a way. So a number of chickens and rabbits is total number is 25, and with their legs actually add up to 86, right? Now, if chickens also had 4 legs, if chickens have 4 legs, have 4 legs, right? Then the total number of legs is 25 times 4, 100. 100 is the total number of legs. Now, this actually is 100 minus 86 more than uh, the given total. 14 more than the given total. Now, this 14 came from extra legs given to chicken, right? So we give 2 extra legs to each chicken, right? So if you divide by 2, right, we can see the number of chicken. So if extra legs, the total of extra legs is 14. And if we give each chicken 2 extra legs, and if you divide 14 by 2, we get the number of chickens, 7 chickens. And you can see that it's a very nice solution, right? Okay, now this is what I want you to do, right? A variation of this, right? Can you do solve the problem by thinking if rabbits have 2 legs instead of 4, right? I put 2 dots here. Can you solve the problem by thinking, that rabbits have 2 legs? So we don't give extra legs, right? We take away 2 legs from each rabbit. This is, not physically, right? In our imagination, right? We should be able to imagine things, right? All right. Speaking of imagination, right? So that's the end of all 30 questions. The last hard question. And then if you look at this last page, right? So you have this, there's a nice write-up for you to read. You may not understand this, and this is for your parents, right? So this is actually for your parents, right? Ask them to read it, right? And your teachers and parents. So parents and teachers, right? So they should read this, right? To see the importance of this kind of competition. But then there is this cartoon which is for everyone, right? So this is for all, right? For all. And why? Because this is my favorite cartoon. This is from the Calvin and Hobbes, uh, Calvin and Hobbes cartoons, right? And this to denote, to tell you that you need to have fun in solving math problems, right? This should not be stress to you, right? So this is why this cartoon is there. Just go over the cartoon and see whether you get it, right? Now, Now, I say that we should be able to imagine, right? Now, this tiger, right, is actually is Hobbes. His name is Hobbes, right? This tiger is Calvin's friend, right? This Calvin's friend, right? That's Calvin, right? It is a stuffed tiger, right? But for Calvin, he's his imaginary friend, right? So it is not just a stuffed tiger like it to others, right? It is alive, right? And that's why the artist, actually the cartoonist, draw the tiger like live tiger, right? But when actually others are there, right? When actually Calvin's mother and father are there, the cartoonist actually draw the tiger like a stuffed tiger. But when Calvin is alone with the tiger, it is alive. So he is, his imaginary friend, Hobbes. Okay, so that's it. Hope you enjoyed the discussion, right? And as I told you, if you didn't understand, please go over that problem again, right? Um, and the important thing is that you need to enjoy doing mathematics. Okay, then I'll see you again in another video. Okay, take care. Till I see you again. All right.